Well, hello there, ladies and gentlemen. We're going to use this good old-fashioned Dixon Ticonderoga number 2 right here to work through some Cambridge probability questions. So, well, let's start with this first one right here. Then we're going to run through 5, 6, 7, and 8. Okay, so number 5 says, an ordinary unbiased die has faces numbered 1, 2, 3, 4, 5, and 6, and each Sarah and Terry throw this die one time. Alright, it says to express the fraction in lowest terms. That means you have to reduce. If it doesn't say that, then you don't have to reduce. But in lowest terms, find the probability that, alright, Sarah threw a 7. Well, that's impossible because there isn't a 7. So that would just be a 0. Yeah? So something that's impossible has a probability of 0. Something that is certain has a probability of 1. Alright, find the probability that they both roll a 6. Right? So we want to find the probability that Sarah rolls a 6, and we want to find also the probability that, what was the other guy's name, Terry? Well, that could be a boy or a girl name, I don't really know. Anyway, find the probability that they both roll a 6. Well, this is 1/6, and that's 1/6, right? So we want to find the probability that this rolls 1/6 and that rolls 1/6. That would be 1/6 times 1/6, right? And so that, not very good at math, but I do believe that that would be 1 out of 36. Good to go? All right, so now, next up, Buttercup. It says, find the probability that neither threw an even number, right? So for the Sarah girl, that would be a 1 or a 3 or a 5, right? And so that would be a probability of 1/2, because half of them are even and half of them are odd, right? And same thing for Terry would be probability that Terry threw a 1 or a 3 or a 5 is also 1/2. So finding the probability that they both threw an odd would be 1/4. 1/2 times 1/2. All right. Next up says, find the probability that Jack threw exactly 4 more. Oh, sorry. Find the probability that Sarah threw 4 more than Terry. The probability that one threw 4 more than the other. So that would be the probability of 4 more. So that could be like a 1 and a 5, right? Or a 2 and a 6. That's it. So probability of 1 and a 5 would be this. Probability of 2 and a 6 would be that. So it's 1 out of 36. That's 1 out of 36. That equals 2 out of 36, which reduces to 1 out of 18. There we go. So, good to go? Good to go. So here's the deal with this one. It says, find the probability. Here, let me show you. The question says, find the probability that Sarah threw exactly 4 more than Terry. So that would mean that, let's get this focused a little better. That would mean that if she threw a 6, that the other one would have to throw exactly a 2 or a 5 and a 1. So the probability of getting a 1 and then the other person getting a 5, that's an and, so that would be multiplied. So that's why it's 1/6 times 1/6. Same here. Probability of a 2 and then the probability of 6. That's also multiplying. But the thing is, the reason we're adding these together is because there's 2 ways for this to happen. It could be this way or it could be that way. And that's why we're adding. All right. Next up, let's do the spinner question right here. So we got this spinner right here, right? It says that 2 unbiased spinners are used in a game. One spinner is numbered from 1 to 6, the other is from 1 to 3. So 1 to 6 and 1 to 3. The scores are multiplied together, and the table shows all of the possible outcomes. So it says, find the probability that the outcome is even, right? So that's 2, 4, 6, 8, 10, right? Anything divisible by 2. The only thing that's tricky about this is that it is very easy to double count. So we've got all these even numbers here, so that's 1, 2, 3, 4, 5, 6, right? 7, 8, 9, 10, 11, 12. That's 12 out of 18, or 2/3. Now this one doesn't say to reduce, so either answer would be appropriate, right? Okay, now the next question says, when the outcome is even, find the probability that it is also greater than 11. So there's this right here, then the outcome is even, right? So we just found out that there are 12 even numbers, okay? So we're only considering the even numbers. We're now going to see that the outcome is greater than 11, so that would be 12 or 18. That's it. It's 1/4. 12 or 18. So, yeah, find the probability that the outcome is greater than 11, given that it's even. There we go, 1/4. Okay, next up, let's do this one over here. So we've got these cards, Adam and Daniel. It says Adam writes his name on 4 red cards, so these gray things are supposed to be red. Daniel writes his name on 6 white cards, right? So Adam and Daniel, right? Find the probability of each of these following things, right? So one of the 10 cards is chosen, so we're just choosing one, and find the probability that the card has a letter D. Well, there's 2 of them, so that would be 2 out of 10, right? So 2 out of 10. Find the probability that the card is red. Well, that would be 4 out of 10, because there's 4 red cards, right? Okay, so we got 2 out of 10, we got 4 out of 10. Now check this out. Cambridge questions are often written like this. You see how we had this one right here, find that the probability that it's got a D is 2 out of 10, and then red is 4 out of 10. So check this out. The next question actually uses information we just discovered in the first 2 questions. And this is a common thing that's done on paper for questions for Cambridge, is they will ask you a couple of simple questions, and they'll ask you another question that requires you to put all that together. So the card is red, or, that means we're going to add, the letter is a D. So it's red or it's a D. Now, this one is a little tricky right here, right? The reason that this is a little tricky is because we could easily double count. Do you see? Because this one right here is red and D. So check this out. The probability that it's red, we know, is 2 out of 10, right? The problem is, or the letter is a D. So that's 2 out of 10, right? Oops, sorry. The probability that it's red is 4 out of 10. My fault. My fault. The probability that it's red is 4 out of 10. 1, 2, 3, 4 out of 10. But one of those is a D. So there's one other way that we could have this or this satisfied, and that's with this card. So we have 1, 2, 3, 4, 5 out of 10, or 1/2. Yep. Okay. The card is red and is we're going to multiply, and the letter on it is a D. Do you see? So this is going to be multiplying. Well, actually, we can do this one a little simpler. So let's read that again. It says the card is red and the letter is a D. So how about we rewrite that and say, what's the probability that we choose a red D? Well, that's just going to be 1 out of 10. Because there's only one of them, right? Just one card that's a red D. So there we go. All right. Next up, Buttercup says the card is red and the letter is an N. Well, there's only one N, and it's not red, so that's 0. That's impossible. There is no way that could happen. All right, now, Adam chooses a card at random, and then Daniel chooses one of the remaining 9 cards. Okay, so give your answers as fractions. Find the probability that the 2 letters are both a D. All right, so now, to get a D, there are 2 out of 10 ways for the first card, right? So Adam chooses one, he keeps it, then Daniel chooses one. Well, if Adam chose a D, now there's only one left, and there's 9 cards left. So that's going to be 2 out of 90, or 1 out of 45. Do you see? So Adam chooses a card at random, and then Daniel chooses one of the remaining. Find the probability that they are both a D. So There's 2 possibilities out of 10 for the first card drawn. After you choose one card, there are only 9 left, and there's only 1 D left, so 1 out of 45. Now, probability that they're both an A. Okay, so let's do that one right here. All right, find the probability that they're both an A. Well, here we have 3 A's, right? So in the first one, there's 3 out of 10. Now there's 9 cards left, and 2 of those. You see? We can reduce that by 3. So that would be, actually we could reduce it by 6, right? But yeah, so 2 out of 30 or 1 out of 15 for them both being an A. 1 out of 15 if it's reduced all the way. Okay, so just to make sure we got this right, they're both an A. So Adam chooses one first. There are 3 chances that he chooses an A, 3 out of 10. Now one of those is gone. There's 9 cards left, and 2 of the cards are still A's. So we're multiplying because we want both things to happen. And then 6 out of 90 reduces to 115. All right, now find the probability that they are both the same. So this is a situation where it's just like we talked about earlier, where they asked one question and they asked another, and then we're going to combine those. So the probability, I shouldn't have erased it, right? The probability of this one right here was 1 out of 15. It was 6 out of 90, right? Whereas the probability of them both being a D was 1 out of 45. 1 out of 45. So I'm going to go ahead and reduce this. So this was 1 out of 45, and the other one's 1 out of 15. So 1 out of 45 was if they're both D. They could also both be an A, right? So they can both be a D, because there's 2 D's. They can both be an A. That's it. There's no other repeated letters, right? So they could both be a D, which is 1 out of 45, or they could both be an A, which is 1 out of 15. Now, if we want to get a common denominator, that's 3 out of 45, so that's going to be 4 out of 45. So the probability that they get the exact same card is 4 out of 45. And the reason we know that, like the thing that we can do to make that easy is look at the last 2 questions. Those are actually a clue. So once again, they are both choosing a card one at a time, and they're the same. So it either could be an A, because we have multiples of A's, or they could both be a D, and that's it. All right, now, here's the thing. The probability that they are different would take some work. It would take some work to figure out how to set that up. But they're either the same or they're different. Do you see? So the 2 cards are either the same card or they're different cards. And so the probability of them being the same plus the probability of them being different have to equal 1. You see? These have to equal 1. So 1 minus the probability that they're the same is the probability that they're different. So that's 41 out of 45. The probability that they are different is going to be 41 out of 45. Okay. So moving on to the last one. Last one we're going to do here. All right, hold on. Let me get this gone. Beautiful. All right. So this is my personal book, so that's why I'm writing it. But either way, I'm going to erase it. So next up, let's do this one right here. So we've got this tree diagram right here, and it says the tree diagram shows a testing procedure on calculators taken from a large batch. It says each time a calculator is chosen at random, the probability that it is faulty is 1 out of 20. So 1 out of 20, 1 out of 20. This would be 19 out of 20, 19 out of 20. You see? So the first part says write down the values of P and Q. No problem, done. Now, 2 calculators are chosen at random. Calculate the probability that they are both faulty. So that would be 1 out of 20 times 1 out of 20. That would be 1 out of 400. So the probability that they're both faulty is 1 out of 400. Okay, now, find the probability that exactly 1 is faulty. All right, now, I'm going to use some paper here, right? So there's 2, so we got calculator 1, we've got calculator 2. Okay, so we have to find the probability that exactly 1 is faulty. So it's either going to be not faulty for the second and faulty for the first, or not faulty for the first and yes, faulty for the second, right? So This one right here, the probability that this one is faulty is 1 out of 20. The probability that this is not faulty is 19 out of 20. Do you see? And then this one, the probability of that is 19 out of 20. The probability that it is faulty is 1 out of 20. So we're going to multiply these together. This is 19 out of 400, and this is 19 out of 400. There are two ways this can happen. It can happen either that it's faulty and then not faulty. That would be exactly 1. Or it could be not faulty and the second one could be faulty. Do you see? So either of these two ways, so those two combine, whoa, that was supposed to be like one of those curly brackets. 19 plus 19, I'm not very good at math, but I do believe that is 38 out of 400. Now that can be reduced, but it's probability, so a lot of the time with probability, not reducing is going to save you some time, because a lot of the time you have to come back and use these numbers, but that's okay. Next up, Buttercup. It says exactly 1 is faulty. We got that. Now, if exactly one of the first two is faulty, then a third is chosen. Third calculator is chosen at random. Calculate the probability that exactly one of the first two is faulty, which we already did, and the third one is faulty. So here's what we've got. We've got this right here. We've got this is exactly one of two is faulty. Right? Is that. Now the third is also faulty. Well, the probability that any random calculator is faulty is 1 out of 20. So it's going to be 38 out of 8,000. And of course, once again, you can reduce that, but you don't really need to. And that's it. Hope it's been helpful. Let me know if you guys have any questions, and have a great day.